Welcome, everybody. Today's going to be a great stream. We're going to be talking about new science, at least new science news that's been coming out of the world of physics with the bad boy of science, Sam Gregson from the United Kingdom of England, or Great Britain and Northern Ireland.
Yeah, that's the one.
All right. So, what's on the docket for today besides the Lagrangian?
So it looks like scientists at Cdf at Fermilab, so just outside Chicago, which I know you have a little bit of history with.
Yeah, that building's been dismantled. So the CDF building, yeah, it was completely removed and replaced with the Accelerator Technology Development Building, something like that.
I've seen a lot of people saying that the last thing they expected for the new physics debate was a blockbuster result from CDF. The Tevatron that stopped running
in
2011.
Yeah.
So yeah, a little bit of a left field one, but still very, very interesting. So the scientists at CDF at Fermilab, as we say, just outside Chicago, they released a new result last week, and it went into I believe into Science, and they say that the W boson appears to be significantly more massive than the standard model predicts. Now, this is an analysis which has been kind of 20 years in the making, as we say. The Tevatron shut down in 2011. It shows only a tiny difference in the mass of the W boson compared to what the theory says. But because they've got such high statistics, it's a very significant difference on the 7 sigma order. So this is the first conclusive experimental result that is at odds with the standard model, although there's a lot of systematics to consider, and the international particle physics community is not yet convinced that this isn't some sort of systematic error, because the result is in strong tension with other experiments like ATLAS, like LHCb at CERN. So there's going to be a lot of discussion about this and a lot of trying to go over and trying to understand what's going on with this. But
okay, so a little background. We have, let me see, I think my levels are maybe a little bit too high on the sound. So CDF is one of the 2 major detectors at the Tevatron at Fermilab. Tevatron was shut down while I was there in, like you said, 2011, like a decade ago. The CDF detector, everything's been dismantled, or at least pulled apart. So which is kind of what dismantled means. I think the detector is probably still in a big block, probably going to be displayed on the lawn at some point. But it's a detector that had been around for like 2 decades, 3 decades almost. And so it's pretty well characterized. It's common with a lot of these facilities that you have an enormous amount of data that just takes a long time to get through. So it shouldn't be surprising to anyone with much experience that there's results that are coming from those detectors even 10 years after the fact. But there is a lot of, what have you done for me lately kind of issues that you have to face. For example, there's going to be new results coming from Kepler, I know, because I'm on a paper where we're going to be submitting some of these new results. But Kepler is also, a fairly old instrument. It shut down 3 years ago. The actual Kepler mission was almost a decade ago when it stopped. And so there's a lot of, it's good that there's always new results that are coming out of these, even if those results get spread out over time, because there's fewer of them to find and there's other things that are going on. But anyways, it was good for me to see that they're still producing results from the 18 billion petabytes of data that they have from these detectors.
Yeah. So when were you there?
So my official residency was there between 2006 and 2012, and then I maintained an office at Fermilab, but I was officially at Northwestern University from 2012 to 2015. So it was 9 years that I was there.
Because I remember so when I was doing my PhD, and I remember when was Higgs? So 2012. I remember that Fermilab was racing with CERN to try and discover the Higgs, hopefully in their backlog of data. And it turned out they didn't have sensitivity in the right mass range to have found it.
Yeah, there were some of the last seminars that were given off of Tevatron results while I was there was kind of the final look from CDF run whatever and D0. So CDF and D0 were the two major detectors, like Atlas and CMS at CERN, and they were doing a joint analysis of all the data that they had gathered on the Higgs. And basically, if the Higgs was there, then they measured it with a pretty good precision. But if it's not there, then they didn't see it. Because basically, they had ruled out all of the mass space, like all the allowed values of the Higgs mass, except for the region where they were the least sensitive. And it was a fairly narrow region where they weren't sensitive to the Higgs mass. So it's like, if it turns out that the Higgs mass is here, then we wouldn't see it. But if it had been anywhere else, they would have picked it up. And so that was basically the conclusion is, well, if the LHC finds the Higgs, we already know where it's going to be. It's going to be in this really narrow range. So it's really a question of if the Higgs is real or not. If it's real, then we've already measured its mass to a relatively good precision. And if it's not there, then there wasn't anything to see in the first place.
That's a positive spin on the. I bet they were pretty sad that they couldn't.
Yeah, it was like a 3
sigma.
sigma result, which is, compelling but not convincing.
Yeah.
What evidence is basically the way it would be described in the.
Yeah, we particle physicists don't get out of bed for less than sort of less than 3 sigma. Certainly
now
not
astronomers on the other hand, it's like,
yeah.
Oh, this is like a half sigma result. Let's publish it.
Exactly. So this is a very statistically significant result. Maybe if we sort of start right from the start. So maybe there's probably people out there who haven't really heard what the W boson is. What is the W boson and why do we care, I guess, is the first question that people will ask.
So the W boson, there are 4 fundamental forces.
I know the answer, by the way, as a particle physicist, but I'm opening the floor.
We're having the discussion around it. So there are 4 fundamental forces that we know of. 3 of them we have a quantum standard model, and gravity probably is quantum. It's probably also a quantum force like the other ones, but we don't have a theory that has any experimental evidence, and so we'll put that aside for the moment. We're dealing with non-relativistic quantum mechanics here. It's
the child that we put off in the tower, and we never speak about.
It wears a mask, like an iron mask, and we're in the Chateau d'If. So when you have a quantum force, that force is mediated. So you have 2 particles that are interacting with that force. That force is mediated by an intermediate vector boson, or by some kind of boson, some kind of force carrier, a gauge boson. And for the weak nuclear force, there are actually 3 of them. Those are the intermediate vector bosons, the Z and the W plus and the W minus. And so whenever you have an interaction between 2 particles with a given force, that the particle that's exchanged in that interaction carries quantum information with it from one to the other. It carries momentum with it from one to the other. It carries energy from one to the other. And in the case of the W, it also carries electric charge. So this is the only force where the force carrier carries the electric charge with it.
So if you've ever wondered why 2 magnets that you put close together, why does one know that the other one is a north or a south and a north? There's these particles, these bosons streaming backwards and forwards. In that case, the photon for the magnetic interaction. But these force carriers, these bosons, carry force information essentially between different particles. And the W boson is the one that does that for radioactive decay, for example. So it's the particle that's sort of behind the burning of the sun, if you like, and any sort of radiative transition. So here we've got beta decay, so decay of a nucleus to an electron and an anti-electron neutrino in this case. So the W boson is very important for anything to do with radioactivity, anything to do with, it's the only vector boson that also we say changes flavor. So it can be essentially change one particle from one type to another. So you hear, for example, you see a down quark becoming an up quark. It's the only one that does that sort of flavor changing transition. So if you want radioactive decay from one thing to another, you need this W boson. That's very, very important. Do you want to talk about the sort of a little bit of the history of the W boson? I don't know if you know.
Well, I mean, it's basically, if you go back to the standard model of particles, the W is one of the more fundamental ones, but that Z0 is not. So it turns out that if you go to high enough energies, the electromagnetic force and the weak nuclear force actually are different. They're actually the same force. There's a unified mathematical structure that encapsulates both the electromagnetic interaction and the weak interactions. And in that, the fundamental particles in that electroweak theory is the B, and then the W plus, the W minus, and the W0. And when you go to lower energies, then the nature of the interaction changes so that you get a massless photon, and the mass that would have been in the B gets kind of absorbed into the Z. So the Z is actually a combination of the W naught and the B, and the photon is the other combination of the W naught and the B. One of them has extra mass, the other one doesn't have any mass. So, but one of the things that's important, and this is where I'm running to the edge of my particle physics knowledge, but the Higgs, all of these force-carrying particles, there's a combination of their masses that has to be, is it for the weak mixing angle?
So I've got I believe it's, so if I go and find it.
So all their masses are related to each other. So if you have a measurement of one of the masses of the particles, then it affects the mass of the other particles. And they all have to be fixed. The sum has to equal a particular value, or else like the photon doesn't work anymore.
Yeah. So I think if you take the ratio of the masses of the W and the Z0, it only depends on the couplings of the particles to those gauge bosons. So you can get very strong constraints between the masses of the various bosons.
Mm-hmm. And if for some reason that constraint was violated, then it actually means that the photon has different properties than what we measure.
Yeah, it sort of messes everything up. So they do these sort of global fits to all of the sort of particle physics results. Obviously, some particle physics results depend on weak couplings, on electromagnetic couplings, on the mass of the W, on the mass of the Z0. And when you throw them all in together, our entire knowledge of particle physics measurements, or at least particular measurements, you can get really strong constraints that this one can't be outside of these limits because otherwise this measurement wouldn't work. This measurement can't be outside of these limits because then this measurement wouldn't work. So they all sort of feed in together and constrain one another. And in there is the mass of the W, because obviously it's related to these couplings. So it's very, very important to know that W mass, or have some idea of that W mass as accurately as we can get it.
Mm-hmm. And that was something when I was at Fermilab, so this is 20 years ago, the first decade of the 2000s, there was a lot of emphasis on getting high quality measurements of the W mass, because that would constrain the allowed values for the Higgs.
Yeah, so this was a particle that was theorized in the 70s, and then they discovered it. Nobel Prize for Carlo Rubbia and Simon van der Meer in 1984. I think it was discovered in 1982. So Nobel Prize for that, because it's obviously incredibly important for this interaction. And then obviously the expected value of the W is very important. Of the W mass is very important going forward, because it feeds into how it will decay. For example, if you have more phase space, the thing is bigger, it's going to give more energy to the things that it decays into. If it's smaller or less massive, it's going to give less energy to the things it decays into. So
right. So when you say phase space, what you're saying is the more massive an object is. Yeah. So suppose you have an object that's going to split into some smaller particles. If you have a larger mass in the progenitor particle, then there's a wider variety of smaller particles that it can produce, and a wider variety of energies of those smaller particles that it can have. There's more energy to start with, and therefore there's more options to when the interaction finishes.
Exactly. So it looks like they're saying from their measurement that it's a little bit heavier than we would expect from the standard model prediction and from the measurements that we've seen in the past. And I guess the first thing that we have to understand about that is how do they go about making these things? So do you want to tell us a little bit about the about Fermilab, about the Tevatron, and how they went about making these W bosons? Because if you're going to weigh them, if you're going to measure their mass, then you damn sure as well must be able to produce them. So
my understanding is basically that, so you have at Fermilab in the Tevatron, it was a particle-antiparticle collision. So it was protons going in one direction and antiprotons going in the other direction. They would collide. The beams were tuned so that they would collide inside the detectors, the CDF and the D0 detectors. And then you get jets of particles that come off based upon all the interactions that take place between these particles as they collide. So you supply a bunch of energy. The energy that you supply can then be absorbed into the mass of the particles that come out of the interaction. Those particles in turn will decay into some products, and then you measure the trails that those products make through your detector. Typically, when you have the collision, you produce, say, the W. The W only lives for 10 to the minus a zillionth of a second. It's a tiny lifetime.
Yeah.
But then when it decays, it produces these jets of particles that come off, and you basically look at your detector, follow those trails backwards, and locate the vertex where that W decayed. So you produce a W. You don't actually detect the W directly. Instead, you detect all the decay products of that W, and then you can measure the mass of the particle that came from it by piecing together the energies of all the particles that went in, and also the distance from where the interaction took place and where the decay took place. So the interaction that produced the W, that distance from where the ultimate decay of that W into the other particles took place. So the bigger the mass, the shorter the distance would be. I mean, there's a variety of things like that. This is not my area of expertise. I just know enough to be dangerous. So
no, it's fine. It's basically the same idea. Yeah. So we smash these protons, antiprotons together. E equals mc squared. So you smash them with enough energy, you can produce these heavier particles like the W boson. As Jason said, W doesn't hang around very long. It decays into other things like electrons and neutrinos. And then you can look for these various tracks in your detector to try and find these W boson events. So one of the ones that they look for and they looked at in this analysis, for example, is a W boson decaying to an electron or a muon and the relevant neutrino. So they look for a signal where you have a collision, then you have an isolated electron or muon, and then just nothing balancing out the momentum on the other side, because it's a neutrino that you never see. So you see these isolated electrons in your collision, and these give a nice sort of clean signal of W bosons. And as Jason says, you can reconstruct the properties of the W, some of the properties of the W, by looking at these events. Now this one, actually, you talked about reconstructing the W mass. I don't think that's what they do in this analysis. Having looked at the paper, what they actually do, it's really odd. And I'm having a chat to one of the sort of experimentalists tomorrow. Is they look at the kinematic distributions of the electron that comes out from that decay and the neutrino inferred from the missing energy and the missing momentum. And then they sort of infer what the W mass must have been to produce these distributions.
Yeah. So this is actually similar to the way that you would do neutrino mass measurements, where you basically you map out the distribution of how frequently do things come out with a given amount of kinetic energy or something like that. And then you say, okay, here's the distribution of all of the energy that comes out. You don't see very much in the extreme tail. It's really rare to have the most extreme particles. And so you have to basically say, here's the shape of the distribution and here's where it would peter out. And then you infer from that how much energy was there in the initial reservoir, which is the mass of the W. So we know the mass of the electron. We don't know the mass of the neutrino. But then by saying, if we account for all of the energy that comes out in the form of the kinetic energy of all the different particles, then there's this much left over. You add everything together, and that gives you the total W mass that you start with. And that's exactly how the neutrino mass measurements work. They basically say, what's the distribution of decay energies of tritium, and then whatever's left over, that must be the mass of the neutrino that we're never able to detect, because the probability of detecting a neutrino is infinitesimally small when you're talking about, if you're looking at neutrinos from the sun, you might get a couple a day in a football field tank of water. But if you're looking at neutrinos coming from some wimpy human-made particle beam, then you're not going to see something.
So these distributions of the kinematic variables of the electron that comes out, of the neutrino that comes out, they're very, very well. They're at least partially sensitive. They depend on the W mass, as Jason said, depending on how much energy, how much mass you're putting in at the start. So these distributions would look very slightly different if the W boson mass was different. So they model based on all of the physics that we know, what should be these distributions of the output particles if the W boson is a certain mass, and then they shift that model around until it best fits this distribution, and then they say the W mass that best fits these distributions is this, and the W mass that they found is significantly higher than we would expect from the standard model. Now, the interesting thing about this is just how many systematics go into this, because you need to understand the momentum distribution that your detector returns very, very precisely, the energy distributions that your detector produces very, very precisely.
So what you're saying there is you need to understand how sensitive your instrument is to detecting a particle with a given energy or momentum.
Yes.
So that when you actually see something, when you see an individual particle, you can reverse engineer how many that one interaction represents. Because maybe at certain energies you might only detect half of them because of the nature of silicon wafers at this temperature. And so you need to understand your overall sensitivity so that you can take the raw output and remorph it into the underlying output.
So what you see in your detector is the real particle physics interactions underneath convolved with a detector response, essentially. And you need to understand that exact detector response. So when you're measuring a particular momentum, let's say you get a value of 5, the real value might be 4.98 or something. And you need to understand how your detector misaligns that value over the entire momentum range. So you have to have a very dialed in understanding of how your detector works. You also have to have the correct model going in of all the particle physics interactions that you expect in your detector. You have to understand how particles lose radiation and therefore lose momentum as they traverse your detectors before they hit various parts of the detector that then do the response. So there's a hell of a lot of things that go into it.
So you have an electron that comes out, so you have this jet of stuff that comes off of your decay. You have this electron that's moving in a magnetic field, and you can tell it's an electron because of the curvature, but because that electron is curving, it's also going to be emitting synchrotron radiation. And that's so you're saying you've got to take that into account is harder than what you might think going in.
Very, very hard. So you've got to take that into account. You mentioned the magnetic field. So did you map all of that correctly, or are you getting slightly the wrong momentum? All the positions of your straws in your drift chamber that gave you the curvature from the dot that you joined up, are they exactly where you think they are, or are they 1 micron, half a micron misaligned from where you think they are? You have to do all of these tests to make sure that that detector response is either perfect, which it never is, or you've accounted for all of the offsets and combined them correctly. It's just an insanely intricate amount of work that needs to be done. And this explains probably why it's taken 10 years to do, because you have to have such an amazing understanding of your detector and how it responds to various particles going across it, that it's a hell of a lot of work to be able to do. They've looked at things like looking at different decays and seeing that you get the same result as you would from CERN or other experiments, to try and dial it in, see if there's any offsets, all of these kind of things. But it must have taken a hell of a long time, and you have to have a really amazing intricate understanding of your detector and how it responds to things going across it to get that convolution.
And these aren't small detectors, right? These are, you have to understand the positioning of everything for something that's the size of a, size of a small building.
So I guess this is why people are sort of people are a little bit sort of hesitant with it. So I mean, if we just zoom down,
I saw a survey on Twitter with all of the clearly
was that Will's.
Yeah, where it's like, what do you think is going on? And it was basically 2/3 of the people thought that there's probably some kind of mistake, and 1/3 thought it was probably real.
So I mean, if
I would rather it be the 1/3 that find that it's real, but
of course.
But I voted for the other one.
Because we're cynical physicists. That's why. Can you see the systematics there?
Yeah.
Like the amazing amount of systematics that feed into this. So you've got the lepton energy scale. So I guess the energy resolution in your detector. We've got the recoil. So that I guess that's the neutrino resolution, energy resolution. You've got, did you detect all of the leptons that were there? You've got the backgrounds that feed into these models. So there's going to be some other interactions that happen,
cosmic rays and stuff like that. Yeah.
That aren't exactly the ones that you thought they were. You've got, did you measure the momentums exactly right? Were the momentums of the things coming in exactly what you thought they were? So when we throw two protons or a proton and antiproton together, did you get two quarks that smacked together, or was there a gluon that smacked into there together? So when you throw two protons at each other, it's like throwing a bag of potatoes at each other. Not like when you fire two electrons at each other, 2 point particles. You don't know exactly the energy that they hit at, even though you know the energy that you gave to the proton, because the things.
Okay, so that's this parton distribution. The partons are like the quarks that are within the protons, and you don't know, are the quarks actually moving towards each other at the moment of the collision, or are they moving slightly away from each other?
Angle, like, it's just crazy, the level of intricacy. The QED radiation, so that's when a electron was emitted in this reaction, like you said, did it lose a little bit of energy before it hit your detectors, and therefore was its curvature slightly off because it lost some synchrotron radiation on the way to being detected, and therefore the curvature was slightly steeper than it should have been? And then you've got obviously the statistical results. So just an absolutely insane amount of systematics.
So the statistical result, okay, so they have 6.4, and typically the way you would add all these things together is that you have the sum of the squares. Yeah, right. So you square each of these things, you add them all together, then you take the square root, and that's how you get the total. And so in this case,
but that assumes that they're non-correlated.
Right, that they're not correlated. Right. That each one of these uncertainties is its own uncertainty that's unrelated to everything else. Yeah. So when you're doing experiments, and this is actually kind of shown in this table, when you're doing an experiment, you run the experiment until your statistical uncertainty is comparable to your systematic uncertainty. So the systematic uncertainty is the uncertainty that you have from the response of your instrument and all these background type things. So it doesn't make a whole lot of sense to continue running the experiment past the point where your systematic uncertainty is the same size as your statistical uncertainty, because if you do, all you're getting is your systematic uncertainty, and so
you're stuck at the systematic anyway.
Right, so you won't be able to make a more precise measurement because your uncertainty in how your instrument is behaving dominates your errors. And so that's where you go back and you say, okay, now we need to build a new experiment, or we need to make a refurbishment, or we need to correct whatever. So then you go back to reduce the systematic uncertainty, at which point it makes sense to start taking new data, because now your total uncertainty, there's always this trade-off between, is your uncertainty because you don't have enough data, or is your uncertainty because you don't understand your instrument? And then you just keep working on those two things.
And this is an interesting thing for people to realize, actually, because people are saying this is a 7 sigma result. I remember we had the 7 sigma result for like phosphine in the Venus atmosphere. Just because it's statistically different from the expectation doesn't necessarily mean we found new physics, because there could just be an error. Somebody didn't put a particular systematic in here that they should have done, or they miscalculated one of the systematics, and therefore you can have as much statistical power as you like, and you could still be wrong. A perfect example would be the faster than light neutrinos, right? Which was a very high significant statistical result. They were like, we are seeing something here. It's statistically significant. It's just what they were actually seeing was a floppy wire, or a wire that was slightly longer, or was not quite plugged in correct.
And to be fair to the people who discovered the fast and light neutrinos, they said up front, like, we don't understand this. And so anyone who can take a look at this and tell us what we're missing.
I was having a chat actually with somebody on Twitter who worked there during the time, and they were like, half the people didn't even want to publish. They sat on it for a long time, and then eventually it was almost, he said that half the people were almost put it out so that they can put us out of our misery and find what it is, because we need to know. And I guess there's some thought of this as well from CDF, that get the result out there and people will pore over it, and if there is anything that's amiss, the wider particle physics community will find it, and if there isn't, then
there's
better.
Something there. Yeah, 1 second. I think never mind. So somewhere on my bookshelf, I have the 2010 Discovery Magazine Top 100 physics results, or like results in science. And number 1 was faster than light neutrinos. And number 4 was the Kepler mission and all the discoveries from the Kepler mission. And so Kepler was booted down the list. We got knocked off the podium by a result that turned out to be a cable that wasn't plugged in correctly. And
I remember that was about 2010 as well. Because I remember it coming out while I was.
Yeah, that was 2010. That was the same year, because in that same issue, my paper on airplane passenger boarding was like number 84 or something like that. Nice. So I would have been 83 had the faster than light neutrinos been resolved.
Absolutely cheated. Absolutely cheated. So the really interesting thing here, though, of course, is that if you look at this measurement, you can see the CDF measurement, which is a former colleague of mine on LHCb, Will Barter, I think he's now at Imperial, if I get that right. He's put this together. It's kind of unofficial, but gives a good feel. So here's the new CDF measurement, and as Jason said, they've got down their statistical uncertainties, which is the sort of cyan color, similar to their systematic uncertainty. So they've really driven down on their systematics, which is their understanding of the detector, which makes it the most precise measurement of this W boson mass that's ever been made, as you can see, because all of the other measurements that have been made are wider. They have wider error bars. However, the interesting thing is, if you combine all of the other measurements, they very much align with the standard model expectation. If you put them all in a bunch and put them together, they would all very much align with one another and align with the standard model expectation. And then if you then compare them to the new result is a little bit of an outlier. Well, very much an outlier. I think the unofficial estimate was it's 4 sigma away from the others if you bundle them together. Mm-hmm. So this, it's very much in tension with a lot of the other results. So it remains to be seen. It obviously moves up the average of all of those results if you dial it in. Mm-hmm. But there's a lot of people who, as you sort of alluded to, are sort of looking at it and going, there's a little bit of an odd one.
Yeah,
odd one. So like individually, may be good or odd one may be bad.
Yeah, individually, if you compare, that result with any of the other results, it's actually not all that far away. It's 2 sigma away from LHCb, for example. The one that's maybe farthest away is that L3. Is that LEP? L3?
L3, I guess so. That would make, it must be, because the LEP results should be in there. Uh-huh. Or I forget which ones the detector at LEP were.
So, but, I guess the question then becomes, which one has better understanding of their systematic uncertainties?
And I guess CDF can push back and say, get your errors down, bro, and then we'll talk.
Yeah.
So
when you produce a result that's this small, then with uncertainty that's as small as ours, then we can start having a real discussion.
We could have a conversation with you, but until then,
a similar thing happened with big G measurements, I think, where in the 90s, the measurements of Newton's constant were also kind of big error bars and all over the place. And the Etwash group at the University of Washington was like, okay, let me show you how this is done. And they came in and they produced a result with error bars that were, 5 or 6 times smaller than everything else.
Yeah, it's hard to know what's going on. I mean, the reaction that I've seen, as you said, was sort of one of sounds interesting, but not confirmed. I don't know if you can respond to this then. So usually you want to see confirmation in a couple of experiments. Is there any chance of getting anything from D0 on this, an update from D0? I don't know if that's in the pipeline, or if you know anything on it.
Possibly. I would think that they would have coordinated had they done a similar analysis. And the detectors aren't the same, and so this is a detail that you'd have to talk to someone from the collaborations.
Yeah,
but there are differences between the CDF and the D0 detectors where they're more sensitive to certain kinds of interactions. So the same thing is true with Atlas and CMS. There is a D0 result that's on there.
There is a D0 result, but they haven't done the update, I guess.
Yeah, the most recent, like they haven't made any improvements.
So there was a CDF old result, and then this is 4 times as much data. So what? It's going to be twice as accurate statistically. Right,
and that's kind of what you see. The error bars are half the size of the D0 one. So I suspect, maybe there's a D0 result that's coming out, or maybe they had other things on their mind, and then when this one came out, then they're motivated to do something. Because most of the people
if it comes and sits down here, then we can just go back to sleep.
Right.
If it comes and sits over here, then that'll be pretty interesting. I don't even know if such a measure. I'll ask tomorrow. I'm talking to I don't know if you know Dave Toback.
Sounds familiar, but
sounds familiar.
So there's a question about what D0 is. So D0 was another of the detectors at Fermilab in the Tevatron. So the Tevatron had 2 big detectors, CDF, which is the Collider Detector Facility, and D0 is actually the name of the building. So around the ring at Fermilab, there's A0, B0, C0, D0, E0, and I think there's an F0 are the names of the buildings that go around the perimeter of the thing. And so the D0 detector was in the D0 building.
And they're always set at specific points because that are like like divisions of the ring, right? So you can get the symmetry. So for example, CMS and Atlas are directly across the ring from one another because it just makes it easier to get the collisions at set what's the word I'm looking for?
Like locations,
set arcs of the circle, rather than having them just wherever the hell you like. So I think Atlas is at like 0.1, LHCb is at like 0.8, and then like straight across the circle, it's cut into like 8, I think, or something, and then like CMS is at like 0.4, so straight across the circle. So they put them at special points so that when they put the protons into the ring, they're all going to be colliding at the same time in the different detectors.
Right, because they go in pulsed, right? Aren't they?
Yeah, they go in bunches which are separated out in time. So they'll all be able to sort of collide at the same time in the detectors.
Okay. So that's the W particle. What does it imply?
Yes.
There was a thing. Yeah, so what does it mean? If it's real physics, then what does it mean? The photon stops working, and we're all chemistry stops.
So this is where we go into. I'm an experimentalist, so the theory side is something that I'm not too strong on with this, but there's been a hell of a lot of attempts to sort of understand this. Now, Jason, you will accept that anytime we have something like this where a fundamental value changes, what's the answer that particle physicists always come up with?
It's a scalar field.
It's another scalar field. There's a new particle out there, a new force, a new interaction that we haven't taken account of. So there's been a few ideas that there could be, this is another opening for supersymmetry, which just won't die.
The thing that refuses to die.
Which just refuses to die. You can have a modified Higgs sector with an additional scalar field. There you are, which doesn't have any interactions with the standard model particle, so we wouldn't have seen it so far. I've seen things like dark photons restoration of parity in weak interactions. So maybe parity violation is due to this other field that's there that we don't know about. So as always with this, when we're talking about new physics, it's another field, another interaction, another particle that we haven't seen yet that could be doing something in the background. And then
your sound just cut out.
Oh, sorry.
Oh,
so
now it's back.
We're back.
Yeah.
So as always in particle physics, it's another field, another particle, another interaction that we might not have accounted for, which could change things in a small
haven't there
way.
been like 100 follow-up articles from theorists that have been, so basically you have one paper with 100 authors on it that produces a result, and then you have 100 papers with one author on it that interprets that result.
Here's the author list. So I used to be like one of the most prolific paper writers in Cambridge history, not because I'd written loads of papers, but just because every time a paper came out for LHCb in 2010, you get thrown on one of these big lists. So they essentially I think the idea was, and somebody will say that there's a much better reason than this, but I think the idea was that so many people have input on the detector. Maybe you're calibrating the detector. Maybe you're working on some sort of analysis framework that everyone uses. Maybe you're coding up something that everyone uses. That it was just easier to stick everyone on papers rather than trying to disentangle when someone had made a valid contribution to a paper. But for a while, I was on like so many papers. I was like one of the most prolific writers, despite only being involved in like one or two of the actual papers.
Yeah, I agree with the high energy physics approach. I think that having these, it's a long author list, but I think it shows more of what actually goes into producing these results.
Yeah, that's true. So we got that, and then there was a point you were making about that, which was I've forgotten now as I went off into that.
So there have been many papers that have followed on with like, oh, here's what this could be, here's what this could be. Like I had this pet project that I've been, my own personal theory about where dark matter comes from, and so now I'm going to recast how my dark matter particle can explain what's going on here. So
it's interesting you say that, because that's exactly what sort of happened. So as always, when a new piece of a potential new experimental result comes out, the theorists want to jump and try to explain it. Maybe it's a real result, maybe it's systematic, we're not sure, but it gives some scope, and you start to see all of these papers appearing on arXiv like very, very quickly, often sort of reworked of ideas, like Jason says, that people have had, and maybe how they can contribute to this problem. So and a lot of these, as you say, as soon as you start introducing new particles, you can start answering other problems, because these things usually have a lowest energy stable particle that then becomes a dark matter candidate, like supersymmetry. So you start to get a lot of ideas, different particles, different fields that could come in and maybe solve this problem, and then they solve other problems. But really at this stage, I think it's sort of impossible to know. But the idea is that if you start getting a lot of these cracks in the standard model, the W boson mass is too high. Lepton universality doesn't quite work, maybe, as we're seeing at LHCb and other places. If you start getting more and more cracks in the standard model, and you can locate where those cracks are, the idea is that will inform experiments going forward and theory going forward, that, oh, we might want to look in this area, or we might want to look at certain theories that solve 2, 3, 4 different discrepancies at the same time. So the more of these discrepancies that we can sort of mount up and put on a big pile, the more they sort of signpost to where new physics might be hiding. Because we know the standard model can't be the last word, because it doesn't explain things like dark matter, like dark energy. There's a hell of a lot of inputs that you need to put in by hand. We talked about the coupling constants and some of the masses. They're related, but at some point you have to put some of these values in from experiment. So we know that the standard model is not the final word on particle physics, but people have been waiting sort of 50 years to find where
it breaks.
Biggest cracks are.
And so a similar thing is happening in cosmology right now, where there's measurements of the Hubble constant that aren't consistent. And so there's the Hubble tension, and it's been getting bigger as time goes on. It's the difference between if you study the cosmic microwave background radiation, you get one value for the Hubble constant, and if you study
like type 1a supernovas.
Yeah, that's something else along those lines, right? Some other probe that gives you the expansion rate of the universe that you get a different value. And in principle, we live in the same universe, and therefore we should be able to, the results, the different measurements should give consistent results. And the fact that they don't means one of a number of possibilities, right? So now it's up to some theorists to come up with explanations, like here is a way that the universe could behave that would explain both of these results at the same time. Or you go back to the observers, and one of them says, oh, we accidentally plugged this fiber optic cable into the wrong slot. And I mean, but it's not that simple, right? Each one of these is an improvement generally on the past in terms of finding those kinds of bugs in the system, like mechanical bugs in the system, and shaking it out. So what was the other result that we had that appeared?
Oh, I saw something which was this huge lens. I don't know if we can have a chat about that as well quickly. Okay. So let me bring up what I found for there, because I think I sent it to you. So where's my email to you? Yes. Here we go. So this also popped up, and I wanted to get your thoughts on it if we could.
Yeah. So
I don't know if it's particularly serious. I do realize that there's an April 1 on this, so I'm skeptical straight away. Any thoughts on this?
So my understanding is that this has been done before. Not in a space telescope, but I think there's a telescope called Alpaca. Let me see.
So serious research though, right? I haven't been taking it.
And so in this case, it's a pool of mercury, and they spin it. And so then it creates a parabola. And so you have a reflective mercury dish with a camera on top of it. So yeah, it looks like that's what it is, a liquid mirror telescope. So
the big problem here, and James Webb has sort of been an amazing tech demo in this field, is on the ground we can have these huge telescopes, mm-hmm. right? We can have all the
they're easy to tinker with. You can go pull something out.
We can mess with them. We can segment them. We can have big steel stanchions that hold them up, and they sag in their own weight, and we can correct that by putting more stanchions in and all these kind of things. And James Webb, obviously, if you want to take a huge mirror into space, you have to fold it up. You can't just have this huge mirror that you're lifting up on a rocket. It's not going to be aerodynamic. You're not going to be able to get it into space. So with James Webb, they folded up a telescope, and then they reopened it when they got to L2.
And that's kind of the limit of what you can do. I mean, you can't imagine something that was, say, twice the diameter of James Webb going up, unless you did it with multiple launches and then assembled it in space.
But it's really opened that idea, hasn't it? That maybe, because we have been able to unfold this thing, maybe we could get away with unfolding something even bigger, mm-hmm. like you say, maybe in multiple missions, these kind of things. But it's brought that idea of a bigger telescope in space.
Yeah, how do you go from 6 meters to 60 meters?
Yeah, basically is the next question. And I guess people have been thinking about ideas as to how we might do this. So what was the idea with this alpaca and these kind of things? The idea is that what you have like a tank of mercury or a tank of reflective surface, and you sort of
you just spin
balloon kind of thing.
No, you spin the telescope so it's on the ground, and you just spin the base of the telescope. You can't steer it; it only points straight up. But as you spin the base of the telescope, the surface of the mercury forms a parabola, and so now you've got a parabolic mirror that points straight up. But you didn't have to polish the mirror. It didn't take. All you had to do was get a flat vat, fill it up with some, toxic liquid metal, and then spin it and make sure you don't spill as you spin it. And now you've got a 7-inch telescope or a 7-meter telescope or whatever, however big it was. And so you can. So I suspect that this liquid mirror surface, people are saying, is there a way, because with a liquid one, you could imagine it going up like as though you're going to blow soap bubbles, right? You send it up as a long skinny thing, and then you let the ring or whatever expand, drawing this fluid with it. So now you've got essentially a film connected to this wire, and then I don't know how you would get it. Maybe it uses surface tension in some way, and you can put in some guide wires that would produce the right shape that you need from the surface tension of the film or something like that.
So what have they got here? Yeah, it looks like you say, surface quality. So by injecting a liquid that can be solidified into circular frames submerged in water to create lenses literally in a janitor's bucket. So it sounds like the sort of idea that you were saying. The trick is to make sure that the water has the exact same density as the polymer we're injecting, so the forces of buoyancy precisely oppose gravitational forces to simulate the conditions of weightlessness. So it looks like they were trying this on the ground. And as you say, it looks like when you take that into space, that's not a consideration. It just sort of sits there. So maybe if you can spin it, like you say, and produce essentially a gravitational force, a centripetal force, maybe.
Oh yeah, I hadn't thought about that. So
spin it into these.
Yeah, so they have to come up with some mechanism to make the surface curve. But once you've done that, even if it only reflects at one wavelength, now you've got a 100-meter telescope at that wavelength, or a small narrow band. It doesn't take much. H alpha, you can learn a lot from H alpha emission, which is a single line. Of course, if you do high redshift H alpha, then it's no longer a single line. But if you're doing local H alpha of the sun or whatever, then you can get a lot of information out of it. Well,
we just have to put up millions and millions of these telescopes that have slightly different sizes and slightly different shapes, right? And then we're good to go. But yeah, it sounds like an interesting thing. I didn't go too deep into it because I was worried, as I said, about the sort of April the 1st thing. But it seems like this is something that they're testing. And I just wanted to get your thoughts on it, really.
It seems, it's a challenging question. How do you go from 6 meters to even 30 meters in space? And we can barely do that on the ground. So what other options are there? This sounds like totally plausible. It sounds like a totally plausible proof of concept type thing where, what's going to happen is a mission that no one's ever going to hear about except for the people who are working on it is going to be, okay, we've tried this in an airplane, we've tried it in the swimming pool thing. Now we need to you don't want to do it in a balloon, but you might do it in a sounding rocket or, some low Earth orbit thing. So they have, for example, there's some new rocketry companies that will put payloads up into space for like $1 million. And that sounds like a lot, but when you say like the Kepler launch was 200 and something $million. The space shuttle launches were like $500 million. It's expensive to get things up into orbit. And so as long as your payload is pretty small, there are some new companies that are coming online that are doing cost savings in one way or another. And so I could easily imagine a NASA mission where it's basically a small group of people where they're like, okay, try out this liquid thing in space on a low risk. It's kind of high risk, high reward, but it's a low cost. So I guess in that regard, it's a low risk. It's an inexpensive expedition to test something out,
just see if it will work. If
it fails, then now we know, and if it succeeds, then we'll take it to the next stage. We'll go from a 30 centimeter, like a 1 foot telescope, to a 1 meter telescope, and then from there to 10, and then from there to 30 or whatever.
No, it sounds like a really interesting idea. Did you catch? You were talking about low cost launches. Did you catch the spin launch? NASA getting involved with spin launch. Have you seen spin launch?
No, what's that?
So I'll bring it up. So NASA. This came up today actually. So NASA will test the ability of spin launch. So the idea behind this spin launch.
So like a big trebuchet?
It's basically a big trebuchet. So what they have is you put in a little payload that you want to throw into orbit, and then they have an evacuated tube inside, so no air inside, so they can spin it up to very, 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 very high speed in this essentially trebuchet. and then when they get up to a particular speed, which is high enough for escape velocity, they open a hatch in this circle. You can imagine the thing is sort of going around in this circle. They open a hatch, and as the sort of tangent comes round on the circle, it just goes up this pipe, flies off into space, apparently. So
that's got to be a very strong pipe.
Well, yes, and it's sort of asymmetrical. So I'm not sure. Like once you release it, you've got to account for all of that momentum. But it seems like this is another thing that NASA are going to have a look at and see if it's got any legs.
Yeah, if the payload's small, like a kilogram or something like that. Okay, that's.
So I think this is going to be for small payloads. I think they said, and it needs to be something that's pretty robust, right? I don't think you're going to be throwing sensitive James Webb Space Telescope electronics into space like this. But
how fast would that need to be going? Because you're talking about you need to get 11 kilometers per second, right?
So what's he got here? Orbital accelerator uses speeds up to 5,000 miles per hour to rotate the arm. Have we got any other data? No, it just says it gets up to 5,000 miles per hour, which I guess is the sort of.
Oh, okay. Someone mentioned that it also has a rocket stage, so maybe.
That's right. Actually, yes, they are correct in that. So I believe.
Okay, so that's kind of like the experimental things where you like put something on a B-52 and you fly it up and then you assisted launch or whatever.
That's right. It is an assisted launch. That's correct. Thank you for that. Whoever said that in the comments. So it gets part of the way to space, and then they, obviously the air is getting thinner as a sort of Boltzmann distribution as you go up, and as you get higher up, you don't have as much air to go through. They fire the rocket booster. It's easier for the rocket to go through that thinner atmosphere.
So this makes actually quite a bit of sense, provided they can, that you're not damaging it as you're spinning it around. Certainly they can make a wheel that rotates smoothly. I mean, they have mechanical flywheels that have huge amounts of energy in them. So what this does is it means that even if you're just getting it up a mile into the sky, that is the amount of fuel that it takes to lift your fuel a mile up into the air, because the first stages of any rocket is really just designed to lift the fuel up off the ground. And so if you can eliminate the need to lift the fuel off the ground using fuel, then the most expensive inch in your launch is the first inch.
And it gets easier and easier from there, basically.
Yeah, that's cool.
So if you can eliminate as much of the sort of low to the ground, thick air sort of travel, then it should give you significant cost savings, as you say, in terms of fuel, and you've got a lighter payload overall. So
that's cool.
That's the idea behind there. So they're
I'd be down with that.
They're looking at that as well to see if that works. I'm skeptical, but it is a cool thing. So I mean, it's another one of these things where I guess I just say I'm skeptical because I'm a scientist, so I know all the things that can go wrong. But I always, even when I say I'm skeptical, I hope all these things work because it's
it'll be spectacularly cool if it goes wrong. Right? It's like we put it up and then it's like like that. So there's a picture or a film of Randy Johnson, who was a pitcher for I think of the Blue Jays at the time, and he throws this pitch right as a bird came across the thing, and then like the bird just like disintegrates into a bunch of feathers. So you could imagine something, the failure mode of this thing turning into like some spacecraft that turns into a whole bunch of shards of.
You just see a load of birds disappearing, and I guess there's some crazy regulation and stuff that they've had to go through to get this thing going. But I wouldn't want to be too close to this thing when it was operating. But that said, they must have had some success, because if they've got to the stage where NASA is going to take a look, it seems to be another one of these things where it's technically feasible, reasonable. Just remains to be seen if the engineering can work and we can get something that you can replicate and launch repeatedly and make the savings that they say they can make. So
right,
that was another little cool one. So
what else has come out in science news lately? I mean, definitely the W thing has gotten the most traction. I'm trying to think.
So I could go to you actually on one. So I don't know if you saw it on the the BBC. So it was a fossil asteroid. Maybe you saw this one, or maybe you didn't.
Is this like the Close Approach?
No, this one.
Fossil of dinosaur killed in asteroid strike found. Fossil of dinosaur killed in asteroid strike found. That. Okay.
So, have you seen? I guess you haven't seen this one. So
No.
maybe we can look. Maybe we can look briefly at this. So, scientists have presented a stunningly preserved leg of a dinosaur, and they're saying the claim is that the Tannis creatures were killed and entombed on the actual day a giant asteroid struck the Earth. So the day was 66 million years ago, when the reign of the dinosaurs ended and the rise of mammals began. Very few dinosaur remains have been found in the rocks around that time, and the final few thousand years before the impact. So they believe that this is essentially a fossilized dinosaur that was caught in an asteroid.
Pompeii.
impact.
It's like the Pompeii dinosaur.
Yeah, basically. Now, I don't know why they think this is. I would have to have a wider research.
Yeah, that sounds... I mean, here my guess would be that this was a dinosaur that died as a consequence of the climate change that resulted from the impact, because this is talking about the impact site, which I don't know how it's pronounced, but the thing off the Yucatan that was like the last nail in the coffin for the dinosaurs. Yeah. And you know, the impact itself, asteroids aren't that big, right? It's like a billionth the mass of the Earth. And so, but the atmosphere is fairly thin, and so it doesn't take much to change the composition of the atmosphere sufficiently to kill off a bunch of plants. So my guess is it almost certainly did not die from the impact itself.
No.
It died from the consequences of...
It didn't get whacked on the head by the asteroid directly, I don't think.
But instead, it's something that died coincident with the arrival of this thing. So, you know...
it's like you said, it's like the Pompeii, right? Where somebody was... They say like somebody was just walking down the street and they're covered in ash and they're caught in their pose or whatever, or huddled in
so
their
I
house
suspect that you know, this would have died.
There's a bit of the science here actually. So it says the sturgeon and paddlefish in the fossil are the key. They have small particles stuck in their gills. So I guess they found these.
Right. So you would look for a change in the composition from certain elements that are common in asteroid populations that are different, that aren't common on the Earth. So, for example, you can tell the temperature where certain gases will freeze or condense, because if those gases have different isotopes, the heavier isotopes will tend to freeze first, and then the lighter ones will freeze later. And so the ratio of oxygen 16 to oxygen 18 or something like that is in the ice, in the water that condenses into a solid form, tells you about the temperature and pressure conditions that are present. And so what they would do is they would look at this and they'd say, oh, look, the hafnium abundance relative to ytterbium is not the same as what you get here. And therefore, you know, if you look at, I think iridium is actually something that they can, is actually one of the elements where you see the collision, it puts a bunch of dust in the atmosphere that is enriched in some iridium isotope, and then it settles down to Earth. And so now you have this layer in the rocks where there's excess iridium, and that's an indication that, okay, this was space rock that came down and caused this. And so so when they say there's these particles, it's probably, here's my guess, and we can see if I'm right, that there are particles with certain chemical composition, isotopic chemical composition, that are not native to Earth and therefore had to be coincident with the arrival of something from space.
That sounds pretty close to me. So it says that these fish that they found preserved with this dinosaur leg, they had these spherules of little specks basically of molten rock, which were stuck in their gills. So these will have been kicked up when the asteroid landed, and then they settled back to Earth, and they got stuck in these fish's gills. And they said they've recovered these, preserved. And they look at the composition of this material, and it's linked to asteroid impacts essentially. Mm-hmm. So yeah, that sounds like pretty much the
Chicxulub, I guess is the name of.
I thought you were pointing to something else.
No, but I think so. I guess that's the name of this impact crater that's at the Yucatan Peninsula.
What do they call? I think they call it. What do they call it? The KT boundary or something? I can't remember. But yes, it's the one that they believe was the sort of death knell for the dinosaurs, which was this asteroid impact, what must be roughly 65 million years ago, which obviously significantly changed the climate. You get all this rock dust thrown up into the air. The planet cools because not as much light can get through. And
okay, I'm sorry, I was corrected. It's Chicxulub. Chicxulub.
I'll let you off the pronunciation because I didn't even attempt it. So,
well, it's like for some reason, astronomers and planetary scientists in general have decided to make like, what's the hardest word that we can think to pronounce? Okay, that's what we should name this object. So we have like
no, that must be the place name. That must be the Mexican place name.
Oh,
surely.
Yeah, but there's other ones that the evidence is on my favor when it comes to things like Umwamwa and Kawawar and but what they need to do is, if they really want to, take it up to 11, then they need to start using Navajo names for things, or like the Bushman thing. So it's like they
do in X-Files, where they hide all the old extraterrestrial information in Navajo. So nobody can translate it. Yeah, it sounds like a good idea.
Yeah, or the Bushman things where they have like clicks and things like that. So you have now you're like writing it down, and they're using as like exclamation points and pound signs as characters in the alphabet.
That's what I want to see. All these sort of Olmec cartographs of as the name. Little pyramid and a bird and a river going down.
I guess Prince did that too, right? Prince in the 1990s was like, "Oh, here's my name," and it's this symbol.
Yeah, I remember the artist formerly known as Symbol, because he just kept changing it. Yeah, I remember that. Yeah, so this was a really cool little discovery as well. I remember I was talking to Michelle Thaler, or Thaler, I butcher that name, last week, and she was saying that she had to get dressed up as a triceratops to sort of do the NASA briefing for this, which was a lot of fun apparently. So I didn't catch that, but she said they made her dress up as a triceratops for the outreach, so that's fun. But yeah, so it looks like quite a few cool little findings have happened in the sort of last week. Anything else that you saw sort of come up in the last month?
I think there are some things that will be coming out in the next few weeks. We're starting to get results that are appearing on arXiv for this exoplanet conference that's taking place the first week of May, and I think
how's the organizing of that coming along?
Pretty well. I mean, there's a lot of work to do, and but it's coming along, and so far most of the issues that have come up have been able to be managed. But that's going to be much bigger than we expected. So going in, I was like, if we get 150 or 200 people, then I'll call that a success. And we're getting close to 500 people that are registered.
Wow.
So, but we had to sign contracts and stuff like this for the venue and how many rooms we would book. We had to sign that contract like 18 months ago almost, or like over a year ago. And so you're putting a lot on the line in COVID to say, oh yeah, this is what we're going to do. Here's, several digits of money. And so there was a lot of, I was concerned that we wouldn't get a whole lot of attendance just because we weren't sure, I would rather predict and be pleasantly surprised, predict low and then get a higher turnout, and it turned out to be a much higher turnout than we had thought. But it was a pretty big risk, I think. There has to be a first conference that after the pandemic. So I suspect there's going to be a lot of new results coming from there, and that
anyone we know coming.
David will be there, Kipping.
Okay.
And yeah, so there's a lot of people that I know that are going to be there.
Anyone that we both know, but so we both know Dave. Good. Yeah, sounds like that's going to be awesome. So, anything new that you're presenting, or?
So most of my stuff that we're working on is my graduate students' work. I'll be presenting a poster where I'm basically showing all the code that my graduate students have developed, and their posters are going to be, so they developed some code, it's open source, and they're going to be presenting the results of using that code on something else, and I'm just going to have a paper that's like, here's all the new additions to the software domain. We'll see how it goes in the coming weeks. I think it should turn out pretty good. I think it's going to be exciting. There might be some results from, or like preliminary results from, say, Gaia, because we're right around the time frame where Gaia planet results should be coming out. It may or may not happen at this particular meeting, but it should be sometime in the next few months if it's not at this meeting. JWST has probably, there might be new results from JWST where someone says, hey, I just got this picture, I'm going to slip it in and show it to everybody. But then there's also a whole bunch of new stuff from TESS, the NASA mission that followed Kepler. There's stuff from Cheops, which is a Swiss mission that followed Kepler. There's stuff, new results from ground-based observations, and some kind of interesting microlensing results will be coming out, and some new laboratory measurements that have come out that affect how we interpret planets. So,
I assume you saw the Arundel result.
Nope. What is this?
So the single star or single star system at Z 6.2. So it was the furthest ever observed single star or binary, they believe.
Okay.
I don't know if you caught that a couple of weeks back.
No. But
did you not catch that? You didn't catch that one?
No, that would require that I peek my head above the
Z 6.2. So I'm doing a video on this at the moment, so I'm trying to understand caustics and
okay,
these kind of things.
So I did see you send this.
Yes.
So it's basically an isolated star that has been gravitationally lensed, and therefore we can see it.
Yeah. So
did they get a spectrum of it?
No. So they're waiting for James Webb to do the spectrum for them. So
because like the features that they might be looking for in the spectrum would be, you're going to be looking for metal lines. It's going to be in the visible part of the spectrum, but then it's at redshift 6, so it's going to be 6 times bigger.
Down you go. Yeah, down you go.
So instead of being at a half a micron, it's at 3 microns.
So they're struggling to do the spectrum because, as you say, it's been shifted down into the red end and beyond. Mm-hmm. So they need James Webb to do this, basically.
That would be cool, especially if it was something with really low metallicity. Because
so that's the idea, because it's so far back into the origins of the universe, they assume that it's low metallicity, and therefore when they with the biggest constraints that they have, or the best constraints that they have, they assume it's a 50 to 100 plus
solar mass
star.
Yeah.
So it's this huge star, which is probably mostly hydrogen and helium, and therefore they're like it's probably not likely, but it's possible, very low possibility that it could be one of these population 3 stars, some of the very first stars that developed in the universe.
And with those ones, any measurement would be useful, because when there's no metals around, there's less stringent restrictions on how big you can form a star. So when you have a lot of metals, the opacity of the gas goes up. And so when you're trying to form a star with opaque material, the light that is coming from the center of the star, so you have all these photons bouncing around inside the star, they're trying to get out. If you have an opaque envelope of gas coming in, then it limits the size of the star that you can form, because if the star gets too big and too bright, then it blows away the rest of the material. So it cuts off its own food supply. But if you have no metals, so now there's no absorption lines, the opacity is much, much lower, then you can form stars that are, the predictions are that you can form stars that are like 1,000 solar masses or something like that. And those don't exist at all today, because it doesn't take much contamination to all of a sudden change the opacity and then limit what you can form.
So they don't think this is a population. Well, they think there's a small probability because it's a bit too late.
Mm-hmm.
But they're like, there's a possibility that it could be on the edge of a cluster and it didn't accrete a lot of metals. So maybe hand wave.
Mm-hmm.
Certain models suggest that maybe it could be. But very, very
that is cool.
When they get a spectrum, we'll know more.
I hope that they have time, because
they do. So I asked this question. So it's really cool. They do have the telescope time.
Oh, but it's more than just the telescope time. It's also how long is it going to...
I could answer that as well. Answer that as well. So if the thing is racing away from the line of magnification at the fastest rate that they estimate, 10 years.
Okay.
So they've got 10 years.
Before it's no longer aligned, and then the lensed image will disappear because it's no longer aligned with the lensing object.
That's what they estimate if the thing is literally racing like the worst
in the worst case. Okay.
And then I think they estimate something like 10 to 15 years. And one of the reasons for that is because it's been so stable over the last sort of couple of years or 5 years of Hubble measurements, which tallies with their lens model that it's in a particular region of the sort of...
Yeah, I mean, if it's flat, then there's only so many flat parts of a lensing signature.
Basically. Exactly. So they think that they're going to get 10 to 15 years, but as you were sort of alluding to, you want to look as soon as possible, because if you don't have the right alignment or they go out of alignment, then
you don't see it anymore.
That's the end of it. But you'd imagine, right, naively, the further away it is, the longer that alignment should stay, because you've got bigger circles that are sort of overlapping.
Yeah, because it's an angular thing. It's not a linear thing.
It's an angular thing rather than a linear thing. So you'd imagine the huge distance, if it's further away, it should last for longer. But that's...
Mm-hmm. Yeah, that's so what I mean by that is that because it's within the line of sight to some angle that gives you the lens. And so the farther away it is, the farther it has to physically move in order to create a large change in the angular position that you see in the sky. Yeah. So it'll be, a lot of these new technologies that we have available are really producing science that I didn't anticipate. So another example would be, how long have we had kind of all sky surveys that are able to detect small asteroids? The answer is maybe 20 years. Okay, so in 20 years, we've already seen one object that we know has come from outside of the solar system. And it was pretty big. And so as you move into an even bigger all sky survey or a more comprehensive all sky survey, how many more weird things are coming into the solar system that we didn't know about? How many more kind of strange effects are there to observe now that we actually have the equipment that's capable of observing them? So that's pretty cool.
Do you know one other cool thing? I don't know what your time constraints are. How long have you?
I got a few more minutes, and then.
All right, let's have a very quick look. So, if I go to something you might enjoy, so if I go to
this is one of my favorite YouTube channels.
It's my favorite one. Anyway, so I had a chat with Julian Girard about the look of various star fields compared to old experiments. Mm-hmm. So if you look at, I thought you might get a kick out of these or want to comment slightly.
Hey, that's the dark energy camera. That was the...
exactly. So let me show you this. So this is JWST, the new measurements, versus WISE. So imaging exactly the same field. So if you take the same positions in space, imaged with WISE and with, so we'll go back for that because I went off it a bit quick. So if you take the same field imaged with WISE and with JWST, you can see the huge improvement from JWST, because you're going from a smaller instrument to a much bigger instrument.
Yeah, right? So WISE is the Wide Field Infrared Explorer,
something like that, and it's only like I think it's a 30 centimeter or something.
Yeah, that's pretty standard size.
And you're going up to
6 meters.
6 meters. So it's literally like removing Vaseline from the lens or just sort of putting your glasses on, the change. So in the WISE image, you can sort of see that there is stuff there, right? But you don't know what it is. So this is like the WISE image, the full WISE.
You can see the star, and you can see some blobs.
You can see some blobs, but it's like, what is it? Is this a galaxy? What's going on? And then as you go to JWST, you see them all come into sort of nice focus when you do that transition between the two. Then we moved on to the dark energy spectroscopic instrument, which you recognized. And
so that's the Mayal telescope, which is the dark energy surveys on the Blanco telescope, which is in the southern hemisphere, and the Mayal telescope is the sister telescope to the Blanco telescope, and that's where they're putting Daisy. I think it's in Arizona. And
then if you look at, well, even in Arizona, where the air is very dry, and so I think I'm getting that right. You can see the difference again. So this is the problem here, though, is obviously the atmosphere, right? So this is a ground-based telescope. You're looking through the atmosphere, and you can't see pretty much anything. And then when you go to the Webb, you can see that there's probably some sort of galactic merger going on up at the top here. So amazing sort of improvement between the old and the new. I think we got a really good one. My favorite one's coming up, though. So that was Webb. Then we got the Sloan Digital Survey. Yeah, which you mentioned. So here's the Sloan from the ground base, and the white box. I'm going to show you the same white box in James Webb in a second. You can see there's like 1-2 stars, maybe. I think they said if you really zoom in, there might be a galaxy that you can kind of see in the box. And then as you move to the same box in JWST, you can just see that all of this stuff just immediately pops out that you just couldn't see in the Sloan. It's just a black box with a couple of white fuzzy blobs. And you go to the same box with JWST, and all of this stuff pops straight out. So really, 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 really cool. But I like just seeing that improvement between the old and the new. And then maybe my favorite.
Well, and then if you look at the difference between the old and the older, you get the same kind of effect.
You just see nothing, just a black box. So, and then my favorite one was the Spitzer. So maybe if you
because that's the most directly comparable. Spitzer is the most directly comparable instrument to JWST.
So do you want to comment on that a little bit, and then we'll
so Spitzer was an infrared telescope. It was originally called SIRTIF, the Space Infrared Telescope Facility, and then back then you would name something after it launched. And so James Webb was actually the first mission where they named it kind of before it launched, with a flagship mission. Usually it would be, you have the working name, you launch it up, then you christen it, whatever it's going to be called. So GLAST, the Gamma Ray Large Aperture Space Telescope, was
why was that? Just in case it like blew up on the pad or didn't make it and they didn't want to...
No, I think maybe there's some of that to it. So it was originally, James Webb was called James Webb Space Telescope because he was really instrumental during the Apollo mission, and they're like, oh, no one would ever cancel a mission that would... It was the concern, I think, early on was that it was so ambitious that it would be easy to cut, kind of like the superconducting super collider. And so if we name it after someone who was really pivotal in the history of NASA, then...
It looks bad if it doesn't.
Yeah, then it's like you wouldn't cancel this. And so then they switched, and now all of a sudden they're naming a bunch of telescopes before they turn on as well. So what was called W first is the Nancy Grace Roman telescope. So anyways, this is politics. When you mix politics with anything, you get politics. Politics is like infinity, right? You add infinity to anything and you still get infinity when you're done.
Politics plus science is
still politics. So anyway, Spitzer is the infrared counterpart to Hubble. So Hubble was one of 4 great observatories. There was the Hubble telescope, the Spitzer Space Telescope, the Compton Space Telescope, and the Chandra Space Telescope. Compton was gamma rays, Chandra was X-rays, Hubble was invisible, and Spitzer...
Oh, yes, I remember, because Dan Wilkins, when I talked to him, I think that mentioned Chandra or Chandra came up in one of his...
And Spitzer was the last one, and it was the infrared telescope. And so... this was the premier infrared telescope up until James Webb. And so James Webb also being an infrared telescope, that's why its mirrors are gold instead of silver. So the James Webb Space Telescope is the successor to Spitzer. And the reason you want to go the reason you want a successor to Spitzer is because with Hubble, you're limited in large quantity by the opacity of the dust. You're limited by looking at high redshift stuff. And if you want to study something at high redshift, then whatever features in the optical band is now in the infrared. And so it's actually the infrared telescope that gets you the deep, ancient history of the universe.
So James Webb is basically in some
redshifted
ways, Hubble. It's a redshifted Hubble. It's a visible telescope for the ancient universe, though. So if you want to sort of sell it like that.
So Spitzer was a meter and a half, I think. They had to shorten it down because it went over budget, so they made it a slightly smaller telescope. But it's like a meter and a half telescope in the infrared. And so this is going to be comparing Spitzer at a given wavelength with, I think, James Webb at the same wavelength.
Yeah, I think there's a slight difference in the wavelength, but essentially, as you say, comparing like with like apart from size in the same field. And then if we run it, let's run it now. Like an amazing improvement. So again, you can see these features before with Spitzer. You could tell there was something there. You just didn't have the resolution. So if maybe we focus on this, you can see that this becomes
two
different galaxies.
With
Whereas
structure.
here you're like, maybe there's two things. Oh, there's definitely two things as you come. So I can kind of sit watching this all day trying to work out sort of, is there two things here? And then you just see them separate out into two or three different things from what they were. But you can see that, you can roughly see that there's something there, but you can't really get the idea of what's there. And a load of other stuff sort of pops out. The interesting thing that Julian mentioned to me with this is that you actually see the spoke structure in Spitzer as you see with James Webb, because it has this same Y bar that's holding the
instruments in place
mirror in front of the primary mirror. So you get the same sort of spokey structure. It's just not as focused, not as highly resolved, because it's a smaller telescope. But it's just amazing to see the improvement, as you say. And it would be equally interesting to go back and see backwards in time to just see how far we've come from there. But I really enjoyed seeing those, just to see the comparison between the two, and it was some really
that is cool
little bits of work.
So we'll see what comes out. In this year is going to be some big announcements, probably from Webb, with the first results in a whole bunch of different areas. So we should
get together when that happens and look at the
year in review
images and see what we can see.
Do a year in review of all the discoveries from the new instruments that are turned on. Sounds good.
Definitely. I was gonna say there was something else. Oh yes. So final thing, just before I let you go, something I had been thinking about, and I thought it would be right up your alley. You might be interested, you might not be, and I mentioned it to Dave as well. You remember the sort of golden disc? Somebody mentioned this on Twitter. The golden disc that went with was it
Pioneer
or Pioneer that Sagan sort of consulted on, didn't he? And it was like, what would be the message that we wanted to give to an extraterrestrial if they picked up Pioneer outside the
coordinates to find the Earth, definitely,
basically. And things.
So Voyager had one too. So
Voyager, that's right.
So both Voyager and Pioneer had some version of it. Voyager's was more advanced because it was a decade later.
So somebody asked the question on Twitter, and I'd been thinking about it previously, so I thought I better bump up this idea. What would we put in one nowadays? Would it be any different? What would you include in it? And have things that have changed since the first one was made required an update, or is it still as it should be? So that, I guess that is a question I pose to you, and might be one where we sit down, maybe with yourself, maybe with Dave, and have a think through this, what we might want to put on a new golden disc, probably a different format for a start, because I think it's just it's a
record.
It's a record,
and right? It has instructions on like how to piece it together. Yeah. So like as you play it, is it the Voyager one that has that, where you spin it and it has instructions on like once you get so many bits of data, then you go to the next line, and then you go to the next line after that to put together
something like that. I'll have to read up on it again, but it's all very cleverly constructed so that once you've worked it out, you can be like, oh yeah, that all makes good sense.
Mm-hmm.
But yeah, I thought that might be an interesting thing to visit, and something that might be okay. Sort of up your alley. So
sounds cool.
If you want to have a little think about that, we'll maybe talk about that. But yeah, there's a load of good stuff coming up. I'm really excited to hear what comes up in the exoplanet conference as well. So we should
cool.
We should
we'll
touch base
after that
soon again. Yeah.
All right, sounds good. Hey, thanks for your time.
Pleasure as always, buddy.
Right,
let's
the bad boy of science. Go ahead and give your digits again for everybody.
So if you wanna come and over to Bad Boy of Science on YouTube, or it's Samuel Gregson on Twitter, you're very, very welcome, particularly if you disagree with me. So we like sensible disagreement over on the channel. There's plenty of it to go around. So.
Sounds good. All right. Yeah. Thanks again for all your time. Thanks everybody for stopping by.
Always a pleasure, buddy. Thank you to you, and thank you for those who helped out during the stream with their excellent comments, and just thanks for stopping by.